So to have the first conversation about this course, let's take an example of the speed of a car, and actually just a car, right? So when you apply more gas, the car is going to speed up. So essentially you can view this as gas being an input to the car, and the result or the output is the speed of the car. Input on the left, output on the right. And what is in the middle is the system itself, in this case, the car. So if this is the system, where is the signal? Well, this is the signal. Output signal, input signal. So you have signals, in this case, input and output, at the left and right of the system. In our case, the system is the car. So this is just an example of a real world scenario of how you can think about signals in systems. One another example that I really like is, suppose that we were sitting in a room, right? So let's imagine, let me take my favorite room, Sage 3303. Don't judge. This is my favorite room on RPI campus. The input to that could be my voice. Say, the instructor is standing in front of the class and saying things or lecturing, right? So that's the input to that room. And because of that room characteristics, specifically the sound characteristics, what you hear is actually the output, right? And the system is changing what I speak, and it is maybe attenuating the volume, right? Reducing the volume, because the farther you are in the room, the volume will be lower. It might be adding an echo to my room. It might be, dispersing my voice. So it is changing my voice, which is an input to this. The system is changing certain aspects about my voice, and what comes out is what you hear. So you can think about signals and systems even that in that way. Now, let's talk about an addition to that system. What you can do is, if you are increasing the input signal, the speed of the car keeps on increasing. However, you can be the feedback. So you sit inside the car and you monitor the speed of the car visually. So you have a sensor, your eyes, that are monitoring the speed of the car, which is the output signal, and you are going to apply the brakes as and when necessary to control the gas, which is the input. So this particular system is going to now be called feedback system. Feedback can be positive, can be negative. So if it is negative, that means you're applying brakes, and that means that you are going to go towards stability, right? So you're going to slow down the car. Feedback could also be positive, which means that you are increasing the amount of gas that goes into the car and you are actually increasing the speed. So it could lead to instability of the system. Again, here is your input signal and here is your output signal. And this is your system. And you have a feedback system. The course objective is going to be to understand these fundamentals so that we can analyze and design such systems. This could be, the objective could be help the car move at a constant speed, for example, or help maintain the temperature of a room. So keep monitoring the temperature of a room as a function of time, and change based on the changes in the thermometer, like the monitoring of the temperature in a room. You can change the levels of your air conditioning. You can also apply that so that you can fly an airplane in a level fashion, or you can also think of it as a drone. So that will be our objective for the class. So we need to spend some time talking about the signals, their characteristics, how can we express them mathematically, uh, and then we will go into systems. How can we express characteristics of a system analytically, mathematically? And then we will focus on if there were certain input signals to certain characterized systems, can we find out what outputs we will get? Right. So that will be our focus. Input signal is also called as excitation for the system, and the output signal is also called as response of the system. And then there is of course a feedback system over here shown in dotted line. At the beginning of the course, we will be focusing on just the system: input, signal, output. Input, system, output. We'll be focusing on that. As we go towards the end of the semester, we will be introducing the concept of feedback and stability. So, for now, we are going to leave the feedback out of our discussion. We will be focusing on input, system, output. Actually, you can think about the feedback in terms of a microphone, right? So, if you have a computer volume up and your microphone is also on, there will be a feedback loop created because you have a computer volume up and you have your microphone active. And if there is positive feedback, if the gain of your system is greater than 1, then you will have that very uncomfortable sound because of that feedback happening. That's another example of positive feedback where it could lead to some uncomfortable hearing. And then you reduce the gain of your sound system so that it is still a speaker, but a controlled feedback. Now, what's a signal? It is essentially a sequence of values in time. So if I were to plot a signal, I would first start with an x-axis and a y-axis. Then I would say, what is on my x-axis? I will say time, or simply t. Or I could use t, tau. If I have multiple times that I need to monitor, I could use t1, t2, t3, and so on, or t prime. So all those are notations for time variable. Similarly, you can, by the way, those are for continuous time variable. So these are all for continuous time variable. You could also have discrete time, and we'll talk about this in just a minute, where the variable is n instead of t. How about on the y-axis? Well, on the y-axis, you have the signal itself. So let's say our signal is, let's use f. So I've got f of t on the y-axis, time on the x, f of t on the y. So as the time changes, the amplitude of that signal changes. Some arbitrary signal, right? So at some time t1, it is having a value of what? What is that value? That value is going to be f of t1. At some other time, t2, what is the value? F of t2, and so on, right? So, and it is continuous, as you can clearly see. Every time value has a corresponding signal amplitude value. So this could be the amount of gas your car is getting at every time. It could be a person's height over the course of his lifespan, or his or her lifespan. This could be the room temperature, anything that is a continuous variable, you can sketch that as an amplitude versus time graph. And the sequence of those values in time are essentially the signal, f of t in this case. So example, an individual's heartbeat, individual's voice, an individual's body temperature, etc. Those are all signals that change with respect to time. Now, I write these things because I want you guys to relate to this topic of signals as something that is very real, and you have all those signals as well. So you can think of it in terms of a personalized exercises as well. Light intensity of a room over time, force applied on an object with respect to time, output voltage of a circuit with respect to time. So all of these are examples of what a signal could look like. Notation, we talked about this already, t, tau, t1, and so on. F essentially refers to the whole signal, right? And f of t refers to the value of the signal at time t. Like we said, t1, f of t1, t2, f of t2, and so on. Now, one challenge that obviously we will have is, can f of t be represented mathematically in closed form? Can I use some equations to represent f of t? Well, the answer to that is going to be, well, yeah, maybe for some limited duration of time, you can express real signals mathematically, but in general, you might not be able to do that. At least the actual signal you may not be able to express mathematically. However, its characteristics you might be able to express mathematically. For example, what is the frequency of that signal? What is the amplitude of that signal? So certain aspects about even real signals you may be able to express mathematically. So our goal will be to, instead of worrying about actual specifics for real signals, we worry about their characteristics. Let's take a look at some common signals. And this list, we will add more to this list in the next lecture, which is tomorrow. Let's see. A constant signal. Okay, what does that mean? Constant does not change with time. Can be said as independent of time. So again, I'm going to have a time variable here, and I'm going to have some f1 of t over here. And I will use red with probably slightly thicker line, and I will say this is constant. So no matter what the time is, my signal is constant. In the middle, maybe I can say this is 0. So I've got 0 time right in the middle, and for time less than 0, the signal is, say the value is m. F of t is m. And as you can see, there is no m of t. It is independent of time. There's no m of t there. It doesn't change with time. It's just one constant m. Exactly like a DC voltage, yes. So for all time, that's a constant signal. Next, unit step. Unit means 1, step means it is going up. All right, so let's plot that. I've got my y-axis here. I've got my x-axis here. Time on this guy. And for unit step, I will say f2 of t. Unit step is one of the very common signals, so I will use u of t for that. So wherever you see u of t, you know that it is referring to the unit step. How does it look like? Well, for all the time that is less than 0, it is going to be 0. All right, let's go to red and there. And at time 0, it will step up to 1, and it will remain 1 for all the time that is greater than 1. Perhaps I should also draw arrows over here to indicate that it is going the left and right the same way. unit step. So there should be 1 there. This is 0. How can I express it in a bracket notation? Let's also do bracket notation over here. Bracket notation, also called as piecewise notation. F1 of t equals m for all t. F2 of t. How about F2 of t? Well, clearly there are two regions. One is 0, one is 1. So let's separate it into two parts. One is 0, the other is 1. When is it 0? It is 0 when time is less than 0. It is 1 when time is greater than or equal to 0. So that is bracket notation for unit step. A rectangular pulse. Let's draw that again over here. I've got x-axis, let's see, time f3 of t, red, some arbitrary pulse. I will start at some time and be on for some time and then come back to 0. And some arbitrary amplitude, say I can make a unit rectangular pulse. It doesn't really matter. I can say 2, doesn't matter. And this can be t1 and this can be t2 and this can be 0. So that's a unit pulse or a rectangular pulse that is turning on at t1 and it is turning off at t2. How can I represent this in a bracket notation? I can say f3 of t equals 0 when it is 0 when it is t is less than t1 and t is greater than t2. You can combine those as well. And it is 2 between t1, t2. Actually, a better way to do this would be this. Just say otherwise. So that would be a bracket notation for this particular rectangular pulse. The height of this rectangular pulse may be, it may change, and even the width may change depending on how you change t1 and t2. All right, a sinusoidal function. Well, everybody knows what a sinusoidal function is. Something that goes up and down in a sinusoidal fashion. It is periodic, right? And we'll talk more about the sinusoidal function because we need to discuss about all the details. What are the parameters of the sinusoid function? We'll have to deal with amplitude, frequency, what else? Phase, what else? Offset. I think these four can be all looked at for a sinusoidal function. Wavelength directly related to frequency. So, we combine time period, frequency, and wavelength as one parameter because it's interrelated. So independent parameters, those are the four: amplitude, frequency, phase, and offset. So more on the sinusoidal function a little bit later. Where do you see real signals apart from your heartbeat and your voice and your body temperature, your height? Where do you see real signals in the real world scenario? Well, the radio signal from your AM and FM radio in your car. Well, maybe that was 30 years ago, but that was a real signal. Your the traffic lights, absolutely. Yeah, the signal to your cable TV, the signal that is being received and being transmitted by your cell phone, the signal that is coming to your laptop through an Ethernet cable or from a Wi-Fi signal, the telephone signal, all these are realistic signals. But the point is this: real signals cannot be described mathematically. Even though there is a chance that for a very, very short duration, you might be able to approximate it using a linear model. However, generally, you cannot do it using a mathematical formula. However, their properties can be characterized mathematically. And that's what our focus will be, to look at how do you characterize signals and systems, and so that we can apply all the things that we learn in this course to real world situations. Let's take a look at some signal classification. The first way to classify, or one way to classify the differences between signals, is to classify them as continuous signals and discrete signals. Continuous signals are shown on the left here. A discrete signal is shown on the right here. All I did was I essentially selected, sampled, picked out certain values of my continuous signal, and I represented the same signal as a discrete sequence of values in a discrete signal. So continuous signals, the signals takes values at any time t, at any time 5.0001 time. What is the value? You will be able to find that out. At any time, no matter what the time is, you will be able to find out what the value is. All you have to do is project that particular time onto the y-axis, or in other words, evaluate that particular function at that time, and you will know the value. That's as far as continuous signals go. How about discrete? You are essentially saying that the signal will take values at discrete values of time. Usually we represent this as n. So when we talk about discrete signals, you will see the mention of n, which refers to the nth value. So the first value, second value, third value, and so on. All I did was essentially picked out a few values from the continuous signal. Now, it is very possible that for some particular time value, there is no mention, right? As you can see, just after 15 milliseconds, the line that I drew, there was no value there anywhere. So the values are being selected. So that's one way of going from a continuous signal to a discrete signal. And why would we do that? We would do that to sample. Why would we sample? We are essentially selecting a few signals, few values of the signal, because all the information is unnecessary. For example, if I asked you your height, you are not going to tell me my height was 6 feet at this time and this time and this time and this time and this time. If somebody was asking you to sketch your height, you would probably do, yeah, my height was 4 feet when I was 4 years old, and then 5 feet when I was this year old. So you would essentially pick out some values and you would say, okay, this is enough to represent everything that is to know about my height. In the same way, signals, you can sample the signal to convey all the information that is necessary. Instead of sending, processing, storing all the information about a signal, you do that only for limited time values, discrete time values. More about sampling later on in the course. One thing to note is we have essentially made the x-axis, the time axis, granular. However, our y-axis could still take any value, right? In terms of amplitude, I could still take any value. It's not like I'm limiting the y values. My x values, I have selected only specific times. So that's the first classification. Second classification is analog versus digital. Analog is similar to what we saw in continuous. Signals can take any amplitude value, so there is continuity in the y-axis information. That's your analog signal. However, a digital signal is the one where you have granularity, selection in the amplitude levels. I'm pretty sure several of you have heard of ADC, analog to digital converter. What does that do? It takes an analog signal like the one that is shown in blue over here, looks at the dynamic range of the signal. So, okay, values are from 2.5 all the way down to -2. I'm going to take a look at that particular dynamic range of those values. And then I'm going to essentially do a selection of how many levels do I need. I'm going to have to make it discrete in terms of amplitude. So if I say I have only 8 levels in my analog to digital converter, then I'm going to take the values that are between 2.5 and -2 and divide it up into 8. Oh, this is probably too big. 8 different levels. I may do this uniformly. I may choose to do this non-uniformly. In a simplistic scenario, it is being done uniformly. And then associate the values that are closest to the analog signal to those particular levels. Right? Just to make sure, let me count. This is 8-bit, right? 1, 2, 3, 4, 5, 6, 7, 8. Absolutely. So another term that you can know right now is quantization. So what you do is you quantize these to be 0, 0, 0, 0, 0, 1, 0, 1, 0, and so on, right, all the way to 1, 1, 1 maybe. Again, this particular mapping between amplitude levels and bits that you could use for digital communication is arbitrary. So it can change from one to the other. That mapping doesn't have to be the one that I showed, but I just want to open up that window to you how an analog signal is essentially converted into a digital one. And the next step will be to associate a bit sequence with each of those levels so that you can communicate those values of that signal using bits as opposed to an analog signal itself. So the signal that is shown in blue is analog. It is essentially taking all values in the y-axis or the amplitude. For the digital signal, you have only selected or discrete amplitude levels that are essentially highlighted as a staircase, right? So that's the difference between analog and digital. Next, periodic versus aperiodic signals. A sinusoidal signal like this is periodic. But if it is periodic, mathematically, it has to satisfy this particular condition, which is if capital T is the time period of that particular signal. If it is periodic, then it'll have to have a time period. And if the time period of that signal is cap T, then the signal must satisfy this condition f of small t, the variable, independent time variable, plus the time period t, capital T, the time period, should equal to f of t itself. Let's check. On this graph, I've drawn a periodic signal. This is essentially, I can actually mathematically write this, right? This is 2 cosine, let's see, the time period is 10, so it's 2 pi, frequency is 1 over 10, so 0.1 times t. So the periodic signal, I'm able to write it mathematically over here. I have to be careful here because this is only for t greater than equal to 0. I have not defined it for time less than 0. So this is how it looks like for time greater than 0. In fact, I don't even know what it does after 20. So I might need to limit it. 20 millisecond, by the way. Okay, so if it is 20 millisecond, then this needs to change. So if it is 20 millisecond, that means that the time period is 10 millisecond. That means the frequency is 1 over time period, which is 100 hertz. So this becomes 100 hertz. 2 pi times 100t. So let me write just this, 200 pi t. That's my signal. Let's try to see if that condition is satisfied. I will take some arbitrary point. Let's say I will take 2. At 2 millisecond, I got a value which was slightly more than 0.5. Okay. How about 2 plus cap t? Cap t is 10 millisecond. So 2 plus cap t would be 12. Same value, as you can see. And this particular condition should be satisfied for as long as the signal is periodic. So if it fails, that means it's not no longer periodic. Now for aperiodic signals, that condition, no such time will exist. So for example, over here, there's a triangular signal where no such cap t will exist. It is aperiodic. Does not repeat. All right, let's move on here. The signal classification next we'll consider is causal versus non-causal. So causal, signal f of t is causal if f of t is 0 for all time less than 0. So if I sketch this out, I have, say, an x-axis and a y-axis. This is time. I'm doing it for all of them at once. All of them have a time as the x-axis. The signal f of t is on the y-axis for everything, so I'm not going to even bother writing that. For causal signal, f of t is 0 for less than 0 time. So it would go all the way 0. Let's draw it in red. And then after 0, it might choose to do something like this. But less than 0, it is 0. How about anti-causal? It is just the reverse. So you may have something like this, but it will be 0 for time that is greater than 0. And a non-causal signal is neither causal nor anti-causal. So it is something like this. Zero is an important point over here. So I'm going to mark 0 time for all of them. And I'm also going to write f of t, f of t, f of t here. So that's one way of classifying a signal depending on its causality: causal, non-causal, and anti-causal. Now let's come to the concept of size of the signal. How big is your signal? And one way to find out the size of the signal is to compute its energy. You can also compute its power, but we'll first start with energy. Energy of a signal f of t is defined as do a magnitude squared of that signal f of t. F of t note can be real, can also be complex. So that's another way of classifying a signal: real valued versus complex valued. So if it is real valued or complex valued, the first thing that you would do is do a magnitude of that and square those values and then integrate it over all time. And in a general case, you can apply a limit t tends to infinity. Negative t to t, absolute of f of t whole squared dt. So essentially you are saying that I'm going to take a signal from negative t to t, and I'm essentially going to stretch it apart so that the cap t and negative cap t becomes negative infinity to infinity to compute energy. As a primary formula, we are going to be using this. All I have to do is take the signal, find the magnitude, square it, integrate it for all time. Let's do it for this particular signal that is shown. So we'll do two things. One is we'll do a bracket notation representation of this signal, and then we'll also compute its energy. So f of t, as you can see, has three pieces. Oh, sorry. It is 0 for some time, it is 2 for some time, and it is 2 e raised to negative t over 2 for some time. So those are the three pieces of this signal. It is causal, yes. So we are assuming that it is 0 for all t less than 0. So hold on. No. It is a non-causal signal. Because there are values between 0 and negative 1, and there are values between 2 greater than 0 and less than 0 as well. So it is not causal, it is not anti-causal, it is non-causal. So it's kind of like the one that we saw over here. Let's do the bracket notation. So we got 2, 0, 2, 2e to minus 2. All right, let's do the time periods. Where are they defined? 0, time less than negative 1. 2, 2 is, let's see, negative 1 greater than or equal to t greater than, what is that? 0. And then after that we have t greater than or equal to 0. So we have got three pieces and we've represented f of t in the bracket notation that way. Energy. For energy, we need to use that formula right there. Let's do it. Actually, the signal is real valued. I don't even have to worry about the absolute. I just need to square it and integrate. So when you integrate, you see, I only have to worry about those three pieces, right? In fact, I don't even have to worry about this piece because that will be 0 over there. So that will be 0 for all the time between negative infinity to negative 1. So I don't even have to write that. All I have to worry about is this. EF, energy in the signal, will be negative infinity to negative 1 is going to be 0 plus, what do I have next? Negative 1 to 0. I need to do a 2 squared, so 4 dt. Plus, I have what? More than 0. 0 to infinity. 2e to the negative t over 2 squared. So it will be 4e to the negative t dt. All right, let's try to solve this out. This will be, of course, 0. This will be 4 times 1 time unit. So it will be 4 plus, this will be 4. You have what? E to the negative t over negative 1 with the limits negative infinity to 0. Let's see here. I've got 0 plus 4 plus 4 times e to the negative infinity will be 0 plus, let's see, 1. 8. So energy of this particular signal is 8 units. Let's move on. How about the power of the signal? Well, the power is essentially the average energy of f of t. So what we are going to do is we are going to find the average of the energy. One way to find the average of the energy is simply to sum things up and divide it by the number of things that you are summing up. So the formula slightly changes, right? So you're doing negative t to t f of t squared, magnitude of f of t squared, but you're dividing it by 2 times t because that's for how long you average it out. Why it is 4e to, okay, so let's see. There is a question about why is it 4e to the negative t. So you see this, you did 2e to the negative t over 2 squared, right? So what happens? You get 4e negative t. So there is a square there because there is a square there. All right, I hope that was helpful. Let's move on here. What happened to the division by minus 1? So when you do a plus infinity, it will be no, you guys. So here, let me add. So 2e to the negative t over 2, right? Squared. So it will be what? 2 squared times e to the negative t over 2 multiplied by 2, right? So it will be 4 e to the negative t, right? So when you are raising the powers get multiplied, right? And the other question over here was, let's see, what happened to the division by minus 1? So yeah, I incorporated that. You see, when you integrate 0 to infinity 4e to the negative t dt, it will be 4, the integration of e to the negative t will be e to the negative t divided by negative 1, and this is a definite integral with limits infinity and 0 here. So it will be 4 what? E to the negative infinity divided by negative 1 minus e to the negative 0 divided by minus 1, right? So this will be 4, 0, you see this, plus 1, right? All right. Okay, so let's move on here. So for power, I just want to take a look at the time. We just have a couple of minutes left. Let me just work through this example and then we can finish for the day. So for power, I'm going to have to use this very similar formula, but I'm going to have to average it out for the time period. Actually, the power for a periodic signal like the one that is shown over here, your power is the same as the power of one time period. So let's take a look at one time period. Let's focus on, I'm just going to highlight one time period. That time period right there. So my limits will be what? Negative t to t. Those are negative t to t. So I'm essentially saying set t to be 1. So power in this signal is defined by that formula. Let's apply this to this particular signal. So what do you have here? Negative 1 to 1. Limit t tends to infinity 1 over 2 integration from negative 1 to 1 magnitude of f of t squared. The good news is, again, it's a real signal, so I don't have to worry about the magnitude sign. And the function f of t is, what is it? What is that? It's a straight line passing through 0 with a slope of 1. and I know it's a slope of 1 because you see at time 1 it is 1, and at time 0 it is 0. So it's passing through the origin with a slope of 1. What is that? That is essentially just t. So f of t is t between -1 and 1. So -1 to 1, I've got a t there, and I need to also square it, and then dt. All right, let's work through this integration here. I've got 1 over 2. I've got t cubed over 3 with limits -1 and 1. And I don't even need to do the limit here because t is not going to be a variable. After that, I have what? Half 1 over 3 plus 1 over 3. So 1 over 3. So the power in this waveform is 1/3 units. Power, let's see. Now, well, because we are out of time here, we'll pick it up. We'll revisit the classification of energy and power tomorrow morning. So we'll pick up on slide 21. I'll work through this again with you on 21, and then we'll continue from here uh, in tomorrow's class. So let me stop the recording here, and if you guys have